All right, let's get right into it. You've probably had that moment with a large language model, an LLM, where you just think, wow, it actually gets me. But how does it do that? How does it go from our messy, human words to generating something that sounds so intelligent? Well, in this explainer, we're going to pull back the curtain on the very first, most critical step an AI takes to even begin to understand what we're saying.
I mean, it really does feel like magic, right? You ask it to write a poem, help you debug some code, or even plan a vacation, and boom, it just does it. It feels like it understands the nuance, the intent, and all the creativity packed into our words.
But here is the big secret, the twist in the whole story. These models are totally illiterate. They can't read a single word of text the way you and I can. So that begs the question, how on earth do they pull off these incredible linguistic feats? That's the exact puzzle we're going to solve today.
Okay, so first things first. We have to start with the most fundamental problem here. Machines and humans, well, we speak completely different languages.
See, a computer's native tongue is numbers. It's all structured, logical, unambiguous math. Our language, it's the total opposite. It's messy, it's filled with context, sarcasm, and words that can mean 5 different things. You can't just feed raw text into a computer and expect it to work. That'd be like, I don't know, trying to run your car on orange juice. It's just not going to happen.
So, how do we possibly bridge this massive gap? Well, the answer is a really clever process called tokenization. At its core, tokenization is actually pretty simple. It's just the act of chopping up our messy human sentences into these manageable, standardized little pieces called tokens. Think of it like prepping your ingredients before you start cooking. It's that essential first step. And this diagram, it lays out the entire game plan for us perfectly. Our text gets broken down into tokens. Then, each of those tokens gets turned into a big list of numbers. That numerical representation is called an embedding. That is what the model actually works with. So remember this, text becomes tokens and tokens become numbers. Now, to make this feel a little more real, let's actually follow a prompt through this entire process. We're going to ask the model to do something very, very human. Write an apology email for some kind of tragic gardening mishap. And this isn't just theory. This is literally what happens under the hood. You're looking at a real snippet of code here. Now, you don't need to be a programmer to get this. Just look at this part here. Tokenizer. Prompt. That's the magic step. We're feeding our gardening mishap prompt straight to the tokenizer, and it's converting it into exactly what the model needs, a series of unique ID numbers. And here's what comes out the other side. Our heartfelt, slightly funny request has been transformed into this, a cold, hard list of integers. The word write might become token 14350, Anne might be 385, and so on. Every number is just a unique ID that points to a specific token in the model's huge vocabulary. This list of numbers, this is the language the machine actually understands.
But, as it turns out, there's more than one way to chop up a sentence. And the strategy a model uses to create its tokens, it has huge implications for how well it's going to perform.
So, you've got a few ways you can slice this up. You could split by whole words, which, seems like the obvious choice. Or you could go to the complete other extreme and split by individual characters, or even the raw bytes that make up those characters. Or you could find a happy medium with something called subwords, breaking words into meaningful parts like prefixes and suffixes. And here are the trade-offs. Word tokenization is great for keeping the meaning, but what happens when it sees a word it's never seen before, like a new slang term or a typo? It just breaks. Character tokenization, on the other hand, can handle any word you throw at it, but you kind of lose the whole concept of a word and end up with super long sequences. And that's why subword tokenization is the star of the show. It really is the best of both worlds. So let's zoom in on that middle ground, that sweet spot. Because this clever subword approach is what powers most of the modern LLMs we all use, like GPT-4. A super popular way to create a subword vocabulary is an algorithm called byte pair encoding, or BPE. And the idea behind it is wonderfully elegant. You start with a vocabulary that's made up of only individual characters. Then, you scan a massive amount of text and you find which pair of symbols appears together most often, and you just merge them into a single new symbol. And you just repeat that process over and over and over again. So for example, maybe the letters T and H appear together all the time. Great. BPE merges them into a new Th token. Then maybe it notices that the new Th token and the character E appear together a lot. So it merges them into a single Th token.
You do this thousands of times, and you slowly build up this incredibly efficient vocabulary of common characters, subwords, and even full words.
And this is why it's so powerful. It's both super efficient and really flexible. A common word like apologize can be made from pieces it already knows, like apolog and eyes. But what about a variation like apologizing? No problem. It just swaps out that last token for izing. It means the model can handle almost any word you can imagine, even ones it's never officially seen before.
Okay, so we did it. We've successfully turned our text into a neat list of token IDs. But we're not quite done. A number like, say, 2776 doesn't have any meaning by itself. So how does the model learn that this number represents the whole concept of apologizing?
This is where the second key concept comes into play, embedding. The best way to think about it is like a massive, superpowered dictionary. For every single token ID in its vocabulary, the model has a corresponding list of numbers, and we call that list a vector. The token ID is like the word you look up, and this big, long list of numbers is its rich, multi-dimensional definition that captures all of its meanings and how it relates to other words. And here's how that lookup actually works. It's pretty straightforward, really. The model takes a token ID. Let's say number 42 is the ID for the token apple. It goes to the 42nd row in its giant embedding lookup table, and it just grabs that vector. That vector, which might be hundreds or even thousands of numbers long, is what numerically represents the meaning of an apple to the model.
But here's the final and, honestly, maybe the most important piece of this whole puzzle. The meaning of a word isn't fixed, is it? It changes all the time, based on the other words around it. And this is where modern LLMs are just absolutely incredible. Take the classic example, the word bank. In models like GPT, the embedding for bank isn't static. When the model sees riverbank, it looks at the surrounding context and generates a vector that's related to geography, nature, things like that. But when it sees money bank, it generates a completely different vector, one related to finance and buildings. The exact same token gets a dynamic, context-aware meaning. This is what allows for real, genuine nuance.
So, there you have it. We've gone from messy human language to discrete tokens, then to simple numerical IDs, and finally to these rich, context-aware vectors of meaning. It's a process that literally distills the very essence of our language down into pure math, which, of course, leaves us with one last big question to think about. If all the richness and meaning of our language can be boiled down to lists of numbers, what does it truly mean to understand?